relative permeability. Denoted by letter mu suffix r. So mu r is defined as, or the formula for mu r is mu r is equal to mu divided by mu 0, where mu is the magnetic permeability or permeability of the material, and mu 0 is the permeability of free space or vacuum. So mu r is equal to mu upon mu 0, that means relative permeability is the ratio of magnetic permeability to the permeability of free space or vacuum. Again, it is the ratio of two same quantities. It has no unit and no dimensions. Now, this formula for mu r can be written in different forms, which is equal to, if we multiply and divide this equation by h, then mu r is equal to mu h divided by mu 0 into h. Again, the value of mu into h, in next article we are going to study the magnetic induction regarding the ferromagnetic material such as Rho-Land ring, and in that case the total magnetic induction is given by the formula which is B, and it comes out to be B is equal to mu into H in case of Rho-Land ring. And with respect to this article, we have right here mu H, that means multiply and divide by relation formula, we get mu h upon mu 0 into h, and therefore we write mu into h, which is equal to B, that means magnetic field or magnetic induction, B divided by mu 0 into h. Now again, if in some numericals or MCQs, as we know that the magnetic induction B, which is equal to phi divided by A, that means magnetic induction is magnetic flux per unit area, and by using this definition of magnetic field, magnetic flux per unit area, we can write a new equation for relative permeability. Mu r is equal to B divided by mu 0 into h, but the value of B is phi by A. Therefore, we write here phi by A into mu 0 into h. Therefore, the new formula for relative permeability is phi divided by A into mu 0 into h. And regarding this formula, so many numericals are there that will be taken later. Before that, we are going to study one article in this chapter which is known as Curie's law. And this Curie's law is for paramagnetic substances. So the substances which are weakly repelled by a magnet are called as paramagnetic substances. For example, aluminium, chromium, etc. And for that paramagnetic material, scientist Curie given the law, and according to this, the intensity of magnetization Mz is directly proportional to external magnetic field. Again, this intensity of magnetization is inversely proportional to absolute temperature. So if we combine these two relationships, then we get Mz, which is equal to capital C into B external divided by T, that where the C is Curie constant. So for paramagnetic material, the Curie's law is Mz is equal to C into B external divided by absolute temperature. The same expression can be written in another form, as we know that Mz can be represented by another same property called as intensity of magnetization, that is I. So Mz is replaced by I is equal to C into B external, that means external magnetic field, and this external magnetic field is nothing but it is magnetic intensity, that means capital H, and divided by T. Again, rearranging the term, we write I divided by H is equal to C divided by absolute temperature. And as earlier we have defined magnetic susceptibility. The magnetic susceptibility is the ratio of magnetization to the magnetic intensity. So the left hand side in this equation is again a magnetic susceptibility Chi m, which is equal to C divided by T. And from this relation we conclude that Chi m is inversely proportional to absolute temperature. So from Curie law we conclude the magnetic susceptibility as well as the intensity of magnetization both are inversely proportional to the absolute temperature, and therefore if we plot a graph between Mz and temperature, or Mz, Chi m and temperature, the nature of graph comes out to be, if we plot a graph of Mz taken on y-axis and absolute temperature taken on y-axis, the nature of graph is like this. For paramagnetic material, this is the graph for paramagnetic material. Again, if we plot another graph which is the same nature, if we take magnetic susceptibility on y-axis and absolute temperature on x-axis, again the nature of graph comes out to be a parabola. So the nature of graph regarding the Chi-M versus T and nature of graph MZ against T are plotted, and the nature of both the graph is the same. Now, by using the Curie law, we can write another relationship. If there are two magnetic fields, if there are two absolute temperatures, and if there are two intensity of magnetizations. Suppose that the paramagnetic substance has magnetization Mz1, and corresponding to this magnetization, the magnetic field is B1, and temperature, absolute temperature is suppose T1. For the paramagnetic sample, if the intensity of magnetization is suppose Mz2 and the magnetic field is B2 and the absolute temperature is T2, then by using Curie's law, we can write the formula mZ1 divided by mZ2 is equal to B1 divided by B2 into T2 divided by T1. So this example, this new formula can be utilized for solving the numericals based on the Curie law. So from Curie law, we have write the formula mZ1 divided by mZ2. That means the ratio of magnetization of paramagnetic substance at two different temperatures having two different magnetic inductions, and if one of the magnetization is known, then another magnetization can be calculated. Now today, finally, depending upon this formula, we have to solve a numerical. Suppose that a paramagnetic substance or paramagnetic sample shows magnetization of 8 ampere per meter. 8 ampere per meter, and when it is placed in magnetic field of 0.6 Tesla and a temperature of 4 Kelvin. So these values are provided for first set Mz1, B1 and T1. For the same paramagnetic sample, if B2 is 0.2 Tesla and temperature is 16 Kelvin, then we have to find the value of mZ2. So this is our numerical for paramagnetic sample shows magnetization which is 8 ampere per meter when the magnetic field is 0.6 Tesla and temperature is 4 Kelvin, and another value of magnetic field induction is 0.2 Tesla and temperature is 16 Kelvin, and we have to calculate mZ2. Now for this we use the formula mZ1 divided by mZ2 is equal to B1 upon B2 into T2 upon T1, and in this formula we substitute the values. So mZ1 upon mZ2 is equal to B1 is 0.6 Tesla divided by B2 is 0.2 Tesla multiplied by temperature T2 is 16 Kelvin and T1 is 4 Kelvin. The next step is mZ1 upon mZ2 is equal to equal to 12. So mZ1 upon mZ2 equal to 12. And finally we write mZ1 upon mZ2 equal to 12. And we have to calculate the value of mZ2. And value of mZ1 is given, which is 8. So next step is 8 divided by mZ2, which is equal to 12. And finally we write here mZ2, which is equal to 8 divided by 12, and this 8 divided by 12 is equal to 2 divided by 3, and unit is ampere per meter. So for this numerical our result is mZ2 is equal to 2 by 3 ampere per meter. So dear students, today we learn in this chapter magnetic properties of matter, such as number 1, magnetization of material, or is also called as intensity of magnetization. Second one, we learn about magnetic intensity. Third one, we learn about magnetic susceptibility. Fourth one, we learn about relative permeability. And finally, we learn about the Curie's law. Thank you very much.